Hello, this is Sean Kelly, Dr. Sean Kelly at Santa Barbara City College, Earth and Planetary Sciences. And this is the material for Chapter 13, which is covering the death of stars. So, number one, do all stars die the same way? Not at all. And so what is the factor, the single factor that determines how a star is going to live and how a star is going to die? And the answer is the mass. Okay, so it's all about the mass, right? This is what it is. It's all about the mass. Okay, so I'm thinking that, let's see, I will go ahead and begin now. All right, so chapter 13, how do stars die? So out brief candle, all stars will eventually die. So every star, we didn't know that, by the way, for the longest time, but stars were thought to be infinite, right? They've always existed, they always will exist. We now know that stars have a certain length of lifetime, and we've already talked about the main sequence life, which is the time it takes, the time that a star spends fusing hydrogen in the core, and that's limited by the mass, right? More massive stars have shorter lifetimes on the main sequence, and less massive stars have longer lifetimes. So we're supposed to memorize three numbers. Let me go ahead and remind you. First of all, our sun, right? How long does our sun have on the main sequence? And the answer is 10 billion years, fusing hydrogen as a fuel, turning it into helium ash. How about a more massive stars? So I asked you to memorize that 100 solar masses, 100 times the mass of our sun, would live on the main sequence for only 100,000 years, right? That's an incredibly short time in astronomical scale, right? And then on the other side of that, what about the smallest mass star that can light itself up with fusion of hydrogen in the core? It's 0.08 solar masses, 8% the mass of our sun. And those stars have a theoretical lifetime. I say theoretical because it's incredibly long, 5.5 trillion years on the main sequence. So that is incredible, right? It's unbelievable. So we don't know if it's true, it's just a model, but it certainly seems that they're extremely efficient at fusing hydrogen, and then they have such a slow rate of fusion that they can last for that long. Okay, so how do stars die? And the answer is it depends on the mass, right? There's a few different ways that stars will die. So let's go ahead and talk about the exciting one first, right? So a more massive star, and when I say more massive, what do I mean? You need to memorize the number that I'm about to tell you. And it turns out that if a star has more than 8 times the mass of our sun, 8 solar masses, then it will go all the way, and it will have a supernova, right? And they're actually this type of supernova that we're describing called a type 2 supernova. Now, there is a very special class of situations with binary systems in which you have a white dwarf and a donor star, and usually it'll be a red giant, but it could be a red supergiant or something else. A donor star, which gives mass to a white dwarf, and the white dwarf will exceed the Chandrasekhar limit. So we'll be learning about that in just a minute, but it turns out that white dwarfs can only get so big. There's a limit to how big they can be, and when you exceed that, you get what is called a type 1a supernova. Okay, so but both of these are incredibly energetic events. They are some of the most powerful explosions we can even imagine. And they come from simultaneous fusion of a lot of fuel, right? So it's very, very fast fusion event. Okay, so let's talk about these two types of supernova. They're really exciting. By the way, our sun doesn't do this, right? Okay. So how does stellar evolution work, right? When you have a fuel, in the case of main sequence, that would be hydrogen, and it is fusing to form helium. The fuel, hydrogen, forms the ash, helium. And then that ash accumulates in the core. As long as we have fuel, the core can, so the fusion process, remember, destroys a little bit of matter, and that matter turns into energy according to the formula E equals mc squared. That energy goes into radiation, which then holds the star up, keeps the star from collapsing. So the force of radiation pressure pushing out balances the force of gravity pulling in. But what will happen is that eventually you're going to run out of fuel. So what happens when you run out of the hydrogen fuel in the core? Well, now the core no longer has a source of energy to create radiation, which pushes against gravity. The core will begin to collapse. Now, it's not going to happen all at once. It doesn't work like that. So when you run out of the fuel, then the core, which is not quite hot enough to support the force of gravity, will begin to get smaller, to contract. Okay, so that contraction of anything, gas or plasma, causes it to heat up. So what will happen is that the core will get hotter. And so that has to happen because it's getting smaller. But it turns out it'll take a while before the temperature will reach the critical temperature needed to fuse the ash. And so that's an interesting point, right? So the core is getting hotter, but not hot enough to fuse the fuel yet. So what does it do? It just keeps contracting. As long as there's no fusion happening, the core will continue to contract. Okay, so I just mentioned these numbers again. Here's a few more, but the idea is the more mass of the star, the less time it has on the main sequence, right? So somehow more massive stars are fusing their fuel more effectively, right? They're faster at burning their fuel, and therefore they're going to burn out faster. So, yeah. Okay, so what happens when you run out of hydrogen in the core? That's actually our sun. Let's talk about a smaller mass star like our sun. And let's talk a little bit about how that will look. So we've run out of, actually I gave it away. Okay, we've run out of fuel in the core. So what happens? The core begins to contract and heat up. And so this is a really wonderful thing, right? Before now, the only fusion that was taking place was inside the core because that was the only place hot enough to support the fusion. But what happens as the core contracts is the core heats up. And now there's an area just outside the core that still has lots of hydrogen that is now hot enough to begin fusion. So we can't fuse the hydrogen in the core because there's none left. But there's plenty of hydrogen. In fact, a lot of hydrogen left over in the star. It's just not in the core. It's outside the core. So it hasn't mixed very effectively. So anyways, what happens then is the hydrogen just outside the core begins to fuse because it's now hot enough. And we call this hydrogen shell burning. So now the hydrogen shell burning is actually going to produce a lot more energy than before. The amount of hydrogen that is fusing is much more than it was when it was just happening inside the core. So what happens if you produce more energy, right? What does that lead to? Well, more radiation. So now the radiation pressure, which has been too small, is now too big. It's bigger than the force of gravity. So what has to happen to the star? Well, it has to expand to compensate for that extra energy. And so our sun will do this right after it finishes fusing the hydrogen in the core will begin to contract and heat up, and then we'll begin hydrogen shell burning. But at that point, we will no longer be main sequence stars. It will not be a main sequence star, it will be a red giant. Now, Phil talks a lot about the details, and in fact, there's more than one stage of the red giant. In our book, we actually talk about it also with different names. I'm going to ask you just to learn about it as the red giant stage, but you can almost think about it as several stages within the red giant stage. And red giant meaning a much, much larger star. So as the star expands, not the core, but the outer part expands to compensate for all the extra energy, it cools off. Remember, expanding plasma or gas will have to cool off. And so the surface temperature goes down, which is why it is red. Okay, it got cooler. Okay, so we have now a red giant. So again, the core is not fusing yet, right? It still continues to contract, but outside of that, we have a beautiful hydrogen layer, which is producing energy to keep gravity from collapsing the star any further. And what will happen is that the core will continue to just contract, until finally it reaches the temperature needed to ignite the helium fuel, right? So that temperature, you don't need to know this, but it's about 100 million Kelvin. The temperature for hydrogen fusion was only 10 million Kelvin. So you can see it, it's a big jump to go from 10 to 100, which is why the core doesn't immediately begin fusing hydrogen. It's going to take a little while. But in that little while, the star will grow and it will be a red giant. But somewhere in that red giant phase, the core will finally reach that critical temperature and will ignite. So that is called the helium flash, right? And so now we've got, not only do we have the hydrogen shell burning, but we're going to have helium core burning. So the star is actually now producing more energy than even it was before. And so it's going to have to do, producing more pressure, it's going to expand even more, and it's going to have to come to a new equilibrium. So it will still be a red giant, but it'll be even bigger red giant. Okay. So let's take a look at the track that we see right here. And so I want you to understand a couple of ideas. Let's go ahead and look at this track. Now it's not rectilinear, it's not straight lines, but it's got a little curve to it. Let's ignore the curve and let's just look at a sideways thing. Let's say that this first part is like a horizontal branch, and then this part is almost vertical. It's not perfect, but you know, for our class, it's good enough. So what you need to be able to tell me is what's going on, right? What's happening in this horizontal branch? Okay, so let's look at the horizontal branch first, okay? So what do you see happening? Well, so what's happening to the luminosity if it's horizontal? And you should be able to tell me that the luminosity is not changing, right? It's horizontal, so it's not changing. But what's happening to the surface temperature? And the answer is it's going down. So how do you produce the same amount of light but have a cooler surface? How do you do that? Remember that the surface temperature is a very strong piece of the luminosity formula. It's called the Stefan-Boltzmann equation. So what has to happen? Well, the answer is if your surface gets cooler, but you produce the same amount of light, the only way it can happen is if you have more square meters of surface to produce that light. So can anybody tell me what that means? You're supposed to get the idea. The star has to expand. And so that's what's going on. It's expanding and cooling, but the amount of light that's coming out is roughly the same. All right, well, that's fine. That's what's happening. And now let's talk about the vertical branch. So you need to understand a horizontal branch is one thing, and now a vertical branch. Okay, so as you go along a vertical branch, what's going on? Well, vertical means that this thing is not changing. The temperature is not changing. It's the same classification of star. So if the temperature is not changing, but what's going on? The luminosity is increasing greatly. Let's think about that now, that little puzzle. If the surface temperature is not changing, but now you're getting more light out, what has to happen? And if you remember our discussion of the red dwarf, red giant, red supergiant, the answer is the star is expanding again, right? So it's kind of two stages where the star is expanding and then expanding some more. And actually, so then what? Interesting, right? This point 3 is a special point, right? Because at point 3, the helium ignites. And now it's a little confusing. You might expect, okay, now it's going to expand even more, but it does a little bit more. It actually changes in slightly different ways. So actually, again, you don't have to worry about all of the details, but let's see if we can understand what's going on. As you go from, this is the helium flash, point 3. What happens as you go from 3 to 4? Well, actually, it gets hotter, right? But the amount of luminosity gets cooler. How did that happen? And the answer is the star contracts again. So somehow that extra energy doesn't actually make it just blow up. It makes it come to a new equilibrium where the surface temperature is a little bit hotter. And then we have a little bit more stuff going on. It does finally expand again and keeps the temperature roughly constant. It's cooling just slightly. So this is from 4 to 5 is almost a vertical branch. Now, the surprising thing is that the helium in the core doesn't last very long. Okay, so let's think about this for a moment, right? This is actually an interesting idea. It took 4 hydrogen ions to make 1 helium ion, right? So the numbers of ions dramatically get smaller. So maybe that makes sense that every stage of fusion is going to be shorter because there's less fuel for the star to fuse, okay? But the process for helium fusion is actually really interesting. I'm about to tell you about it. Actually takes 3 heliums to make 1 carbon. Okay, so 3 heliums to make 1 carbon. And this is called the triple alpha process. Okay, so an alpha particle, if you remember, is a helium nucleus. So 3 of them together, if you put it together, 2 plus 2 plus 2 makes 6, which is the atomic number of carbon. And 4 plus 4 plus 4 makes 12. The carbon 12 that is being made is a stable form of carbon inside of the star. Now that's it for our sun, just so you understand. The helium fuel in our sun's core will turn into carbon ash, but that's it. Our sun will not be able to ever fuse the carbon because it will never reach the temperatures needed. It's about 500 million Kelvin to fuse the carbon. So our sun is going to finish after it uses up the helium core. It will still be able to fuse the hydrogen shell for a while. Sorry, it won't quite be done, but it will never be able to use the core material, okay, to fuse. It will never fuse the carbon in the core. Okay. So anyway, so what happens to our sun? Our sun is actually going to go through a very interesting stage as a red giant. You want to think about a star that is really big. Now, most of the time when I tell people, they just don't believe me, but you really want to understand this is really big, okay? And it makes our little sun look puny in comparison. So as the red giant forms, it's going to expand, and it's going to expand, and it's going to expand. And it's going to eat the planet Mercury. Mercury will be inside of the star, swirling it up, stirring up the material. That's interesting, right? And then it'll continue to expand, and then it will eat Venus. And Venus will be inside of the star for a while before it finally gets ablated away. And then it will expand and it will eat the Earth. We're going to be inside of this red giant star. And then it will expand, and it probably won't eat Mercury. Okay, sorry, Mars. It won't get to Mars. But so we've got at least 3 planets that will be eaten by our sun. So this process of actually being a red giant is actually a very interesting thing. The star is so large and the outer shells are so far away that any little extra disturbance actually causes a bubble of material to be shed away from the star. And so our sun is actually going to be losing a huge amount of mass during this stage. In fact, we think it loses 80% of its mass during the red giant or red supergiant stage. The matter that is very far away from the center is just easily puffs out in these shells of material that will move away from the star. Not very fast, by the way, just slowly move away from the star. So each stage of fusion is going to produce this red giant phase is actually going to be shedding material in every direction until there's almost nothing left, right? Until the hydrogen is kind of going to run out. And when the hydrogen shell runs out and the helium in the core has run out a long time ago, what's left? Mainly just the core of carbon. There may also be a little bit of oxygen. For stars that are slightly larger, they may be able to fuse a little bit of the carbon, so they have a mix of carbon and oxygen. And some people theorize that it may be possible to get almost the pure oxygen core as well. But anyways, you've run out of fuel. There's nothing in the core that can fuse. What happens next? Well, the answer is the core is going to collapse. It's going to collapse because gravity is going to make it collapse. And it's going to get hotter and hotter and hotter and hotter and hotter until something makes it stop collapsing. So the way we've talked about it before, when a star was alive, the force of radiation pressure pushing out balanced the force of gravity. But we can't make radiation pressure anymore because there's no more fusion happening. So what is the name of the force that keeps this thing from collapsing? Well, let's get back to that. What has just happened is that when the core collapses because there's no more fuel, we will get a white dwarf. Okay, so our sun will become a white dwarf. Now, the interesting thing is all those gas clouds that were out there, they're still there, right? And that little tiny ember in the middle, which is now the core of the star that has collapsed, formed a white dwarf. It's a very small little ember. It has a really high temperature. We think a surface temperature of about 100,000 Kelvin. And so it shines with ultraviolet light. And that ultraviolet light hits the clouds of material that are escaping from the star, from that red giant phase, and causes them to light up. And so for a little while, we have these clouds of lit up nebula, and it's called a planetary nebula. So once upon a time, astronomers thought that they were little planets. And then we learned that they don't move and they don't orbit the sun, et cetera. But they have a size to them, right? And in fact, they are clouds of gas that are lit up from that little tiny ember of a white dwarf in the middle, okay? Now, we don't think these last for very long. Actually, now we think maybe 10,000 years, but really not a long time. So, the author says something like 1,000 years, it might be 10,000, but it's really a very, very short time in astronomical terms, okay? So, who was the first person to identify these things called planetary nebulas? And it turns out it's a fellow by the name of Charles Messier. So you want to write that name down. Charles Messier was a very famous fellow, but not for what he wanted to be famous for, which is kind of funny. Charles Messier was motivated because he was inspired by Halley's Comet. So Edmund Halley, remember, had predicted the return of Halley's Comet, and sure enough, it came back. He was gone, by the way, he had already died, but people were so impressed, they named the comet in honor of Edmund Halley. And Charles Messier wanted his own comet. So he was a comet hunter, right? He was looking for comets. And so when you look in the night sky for a comet, what do you see? And the answer is it looks a little bit like a star, but not a regular star. It's a fuzzy star. It has a little fuzziness to it. And so Charles Messier would look for these fuzzy stars, and then he would track them night after night. And if they are comets, then what happens? Well, they get brighter as they come closer to the sun, and they move, right? You can watch them moving. They're orbiting the sun. And unfortunately, these objects that Charles Messier identified didn't move. So that was a little frustrating. They weren't comets, right? They look like comets, but they're not comets. So he began to keep track. He kept track of these locations so he wouldn't waste time anymore, and other people wouldn't waste time. These aren't comets, right? This is not a comet. And what is it, Charles? Well, actually, he didn't have a powerful enough a telescope to see what it was. So these are a list of objects called the Messier objects. There's 110 of them, and it turns out they are really cool targets for amateur astronomers to look at. So if some of you are interested in astronomy, I promise you will enjoy looking at Messier objects. And in a star chart, if you look at a star chart, they're labeled M with a number behind it. So M1 is this one right here called the Crab Nebula, which is actually a really interesting one. I'm going to tell you about that one in a few minutes. I think we've already talked about it. And then we have M2 and so forth. So what did he find? Well, he didn't realize it, but these objects are a rich variety of things. Some of them are planetary nebula. Here's M57. There's a couple others like that. They are supernova remnants. They are globular clusters, open clusters, and then, of course, we will find out they are galaxies. Okay, so it's a whole mixture of things. What did we have? We had supernova remnants. We had a globular cluster. We have planetary nebulas. We have open clusters. We have galaxies, right? All of those cool things. There are a couple boring ones. Don't worry about that. But he did actually highlight a couple of stars, thinking it was more, and all they are is a couple of stars. But most of them are really, really interesting. And in fact, every year around the equinox, the vernal equinox, there's a fun little game that we play as astronomers called the Messier Marathon. And we stay up all night long and we try to see all 110 objects. Now, I've never done that, but actually a few years ago, I got my record, which is 67 objects in a single night. So I encourage you, if you're interested, to try to play that with us. And if you're into it, maybe next year with the Astronomy Club, hopefully things will be back to normal again, and you can come out and stay up all night with us, looking for the Messier objects. Actually, I did want to share with you, I put a link on your Canvas page. In fact, let me go ahead and let me show you that, because it is too awesome for me to ignore. If you click on the chapter 13 support material, you'll see this. There's actually a really cute little thing right here, animation of planetary nebula. But here is the worldwide telescope. And if you click that, you get to this amazing page. It's truly amazing. And I just, I'm not going to force you to do it, but just so fun. And you're in an astronomy class, check it out. If you scroll over under collections, you can find the Messier catalog. And this is actually going to show you not only the object, but where they're located. If I click on this one, M1, it scrolls over to where M1 is and then zooms in. And this actually might be a good opportunity for me to talk about. This is a supernova remnant, and it's in the constellation, if you look down here, the constellation of Taurus the Bull. Okay, and they've got all 110 objects here. So I challenge you, go look at all 110 objects just one time. Or whatever. If you don't want to do it, that's fine. But they are pretty cool. You'll see some repetition. It's some of the same things, but it's really neat. Charles Messier didn't know what he was looking at, and we now have the telescope technology to see the details that he couldn't see. So let me go back to our slideshow again. Okay, so Charles Messier, and let's see. So there is a little bit more. So as we continue, right, at the red giant stage, we're going to eject lots and lots of material, and eventually the core will collapse. There won't be any fuel left, and this material will then send out a solar wind and ultraviolet light, which will excite the gas clouds that are escaping and form a planetary nebula. Now, if you look right here, these are all planetary nebulas. I want you to notice that they're not actually spherical, right? Actually, some are, a few are, but otherwise they have these interesting structures. And we don't know exactly why, but I want to remind you that idea that I mentioned before, that when our sun expands, it's going to eat planets. And we now know that every star has planets around it. So every star that goes through a red giant or a red supergiant phase will do something like this. It will eat probably one or more planets that are orbiting it, and those will stir it up. And they could make something that's slightly asymmetric. Now, when I see jets, though, I actually do think about magnetic field. So I don't know the right answer, and a lot of scientists have put in magnetic field, a companion, an accretion disk. Okay, so there's a lot of different ideas. You don't have to worry about that. But one I would mention is that eating planets could lead to some of these interesting structures. Okay, where would the accretion disk come from? It would come from a neighboring star. So if we have a white dwarf, remember James Kaler, his idea? If you have a white dwarf with a red giant companion, the red giant could feed the white dwarf. And for a little while, the material would orbit the white dwarf in what we call an accretion disk. Okay. So this is the picture, actually. Here's our picture. So it could be that there's a companion. That would be another idea. If you remember, this is a binary star system, and we call it a symbiotic binary because the red giant or the red supergiant is going to give a little bit of matter to the white dwarf. So if you take a look right here, the Roche slope is this position right here. When you go beyond this point, the gravitational force from the white dwarf is actually going to dominate, and it's going to pull the material onto the white dwarf. So then the material will go into orbit for a little while before finally collapsing onto the surface of the white dwarf. So this is mainly hydrogen, this hydrogen material. What happens when the hydrogen hits the super hot white dwarf? Well, it fuses almost instantly, right? And then we get a flash of energy. And remember what that's called? It's called a nova, right? So these are the nova. It happens year after year after year. And what happens is that the energy, the flash happens, but it leaves behind a little bit of material on the white dwarf. The white dwarf gets a little bit more massive, right? The white dwarf is actually a little bit more massive. But let's talk a little bit about what that white dwarf looks like, right? The white dwarf looks like something a little bit crazy, right? So don't worry too much about this. But why doesn't the white dwarf get crushed, right? What stops it from gravity from crushing it any further? There must be a force. And the answer is a little bit tricky. It turns out there is a principle called the Heisenberg uncertainty principle. And this is actually a little bit more advanced than our class is. So we're just going to mention that it's there, but it's a very interesting principle. It says that you can't know simultaneously the position of a particle in quantum physics and its velocity perfectly. You can't. There's always some uncertainty. The more carefully you confine a particle, the more you don't know what its velocity is. The more you know its velocity, the less you know where it's located. This is a weird, I know it's totally strange, but a strange built into quantum physics phenomenon. So when you collapse this core of the star, there's a lot of electrons running around, and it's the electrons which are being confined somehow. And the more you try to confine them into the shape which we call the white dwarf, the less we know the velocity. There's somehow a limit to how much you can push them together. So the electrons are going to keep the star from collapsing. And this is what you want to write down. You want to write down the electron degeneracy pressure, okay? So write this down, electron degeneracy pressure. So the force of the electrons is somehow enough to stop the star, this core of the star, from collapsing any further. So gravity's pulling in and the electrons are like, nope, you can't pull me any further. Okay. So now I do want to compare and contrast. This is a little bit strange. I want to make sure, this is confusing, right? It's quantum physics, confusing stuff. But if you take your hand and you put it on your other hand, it stops, right? And you're like, yeah, of course. But why does that happen? Does this hand ever touch this hand? You might remember that I told you that the hand is covered, or the surface is a cloud of electrons. And my other hand is another cloud of electrons. And what's going on when I try to put them next to each other is the electrons are repelling each other. So the clouds of electrons give the solid feel for surfaces. You can't put your hand through a table, right? Unless you're incredibly strong like the Hulk. But anyways, that is the electron repulsion. It is not the electron degeneracy pressure. That's another part of this force. So not only do we have strength from the atoms having clouds of electrons, but we have these additional electrons which are not attached to any atoms, which are giving the electron degeneracy pressure. Now I'm trying to be as precise as I can without going too high, but you want to write down the name. The electron degeneracy pressure is the force which stops gravity inside of a white dwarf. How big is a white dwarf? So you took a core of a star and you collapsed it. How big is it? And the answer is about the size of a planet, about the size of Earth, right? So if you remember, that's 1/100th the size of the original star. That's how big the core has become. So you take something that could be the mass of a star and you squish it down to the size of a planet. This is incredibly dense. I mean, it's just really, really dense. And you need to know that these white dwarfs are made of carbon, possibly oxygen, okay? Carbon and oxygen are pretty much what you get. And this can only be, this only works with smaller mass stars. This will only happen when the star is less than 8 solar masses, okay? So if it's less than 8 solar masses, it will never be able to really have enough pressure and temperature in the core to fuse the carbon and oxygen. On the other hand, if you have more than 8, then you will use the carbon and oxygen as a fuel, okay? So white dwarf, smaller mass stars. Now, we discovered very early on in the 1930s, actually, something really amazing. A theoretical physicist by the name of Subramaniam Chandrasekhar calculated the biggest strength electron degeneracy pressure. He figured out how big is it. Okay. So anyways, here's the entire picture. You don't have to know the whole thing, but you can see this whole journey that we've taken leads us over here to where we are now, white dwarfs. Okay, now eventually white dwarfs will cool off, but none of them have, right? No white dwarfs have cooled off because the universe is not old enough. Okay, it's going to take a very long time, billions of years, billions and billions, like maybe hundreds of billions. I don't know exactly. It's a really long time. At this moment, there are no cool white dwarfs. If they get really cold, they become black dwarfs. Okay, so white dwarfs turn into black dwarfs eventually, but we have never seen one because the universe is not old enough. If we found one, that would be amazing because it would mean the universe is actually older than we think. But anyways, okay, so white dwarfs. So this is an interesting thing. If you calculate theoretically how big the mass of the white dwarf is, you begin to discover something amazing, that the electron degeneracy pressure can only be so strong, right? There's a limit to how much mass and therefore how much gravity the electron degeneracy pressure can fight. And this is named after Chandrasekhar, Subramanyam Chandrasekhar. You need to write this down. The Chandrasekhar limit. This is the largest mass white dwarf that we can have. If you have any more mass than this, then the gravitational force will be too strong and the electron degeneracy pressure will not be able to hold it back. So Chandrasekhar was able to calculate this, and it tells us that white dwarfs can only get so big. Okay, so that's an interesting little fact, right? Electron degeneracy pressure is only so strong, and if you have too much mass, the electrons can't do it anymore. They can't hold gravity back. So let's go ahead and jump to those more massive stars, and the more massive stars have more than 8 solar masses, and they're not going to stop with fusing helium. The helium becomes carbon. The carbon will become neon, right? So this is actually what we're going to talk about. So I mentioned to you how this works, right? The helium can fuse, and 3 of them get together to form carbon when you're done. It's called the triple alpha process. So you burn carbon, and then the carbon turns into neon, and the neon turns into oxygen, and the oxygen turns into silicon, and the silicon finally produces iron ash. Please write that down. At the end of the sequence, you have iron in the core. Okay, so what's happening is every stage produces a new ash, and then eventually as the core collapses, you run out of fuel, the core begins to contract. Eventually the ash will heat up enough so that it can be a fuel, right? So keep going, keep going. Now you might think this could keep going forever, but we learned a while ago something really important. The most efficient atom is iron 56. So what happens when you fuse atoms and you form iron, you've just created the most efficient atom. Well, what if you tried to fuse iron? What would happen? You would make something that's less efficient. Okay, so back up a step. What happens every stage of the way up to iron? Well, you take your fuel and you fuse it, you make your product, you make your ash. The mass of the ash is less than the mass of the fuel. The little extra mass gets turned into energy according to the formula E = mc squared. But what happens if you try to fuse iron? And the answer is you get something that's more massive. Okay, think about that for a moment. How do you get more mass? Well, same equation, E = mc squared. Instead of heating up the core, what does it do? Fusion of iron sucks energy from the environment and makes the core get cooler. It accelerates the collapse. Okay, so you need to understand an important idea. If you have more than 8 solar masses, then you will go all the way. You will be eventually able to fuse iron in the core. And simultaneously, by the way, you've got all these other shells of burning that are occurring at the same time. We call it the onion skin look, right? You've got all these shells of material that are producing energy. This is an enormous thing. It's not a red giant. This is called a red supergiant. Okay, so it's going to be a really large star. I mean, incredibly large. Okay, so I'm not going to worry too much about size, but it's huge. Okay, and so we run out of fuel, and then we fuse the iron, and then it's over. So what's really remarkable is this process has taken millions, billions, or millions of years, or maybe hundreds of thousands of years at least. And then I tell you something, right? The core begins to fuse iron. And I just told you that instead of releasing energy, it absorbs energy when you do fusion of iron. And that's not going to work. You have to release energy to make the pressure to stop gravity. So this is it. This is the end. As soon as a star begins to fuse iron, a fraction of a second later, it's over. Okay? A fraction of a second. This is really complicated, and I certainly don't understand all of it, but there are some beautiful animations and simulations to try to show you what that looks like. And I would like to show you an animation right now. And this is a supercomputer animation of what is called a core collapse supernova, a more massive star that has begun to fuse iron. And if you look at the timer, you'll notice that this is measuring milliseconds. Let me see if I can see that. There you go, milliseconds up at the top. And remember, that's thousandths of a second. This is pretty crazy stuff. And this is just the beginning. And what's interesting is it's not symmetric. It's got this very organic look to it. It may not be exactly symmetric. And so the explosion that's about to occur, which is called a type 2 supernova, might have jets of material coming out in different directions. It's not necessarily symmetric. So what begins pretty symmetric with very, very tiny little differences will lead to some exaggeration and bulges in one direction or another. But look at this. This is just 150 milliseconds. That's 0.15 seconds, right? This is how long it takes. Okay, so that is kind of crazy. Just to understand how fast this is occurring, okay? A fraction of a second after you begin to fuse iron, it's over, okay? So the core collapses, all of that iron collapses. The other layers try to fall in behind it, and they hit the solid iron core and bounce off, and you get this incredible fusion that's happening almost simultaneously. It's a huge amount of energy. It's incredible. This is a type 2 supernova. And that material blasts away and leaves behind just that iron core. So most of the iron does not get fused, right? Just a tiny little fraction actually ever gets fused. The remaining core is still there, left behind, okay? So this is pretty cool. This is a crazy little thing. So actually, I forgot to tell you something important. Let me go ahead and I want to remind you an important idea. This is amazing. I'm sure I told you one time, but in case you forgot, there's actually some recent experiments that were just done to try to highlight this a little bit. If you take a free neutron, right, and you take it away from a nucleus, it is unstable. Okay, it decays. Okay, and if you remember radioactive decay, it's not radioactive decay exactly, but unstable is a similar idea. It's not going to stay the way it is. So if you take a neutron, how does it decay? And the answer is into one proton plus one electron plus one anti-electron neutrino. You don't need to worry about that so much. Okay, but this is how a neutron falls apart. And what you want to understand is what tells us how this works. The way that this works is governed by the weak nuclear force. So the weak nuclear force explains this. I don't know how that works. I'm just going to write that down. Okay. So the weak nuclear force is the thing that kind of explains why this falls apart sometimes. But I want you to try to go back to the original story that I told you before. Remember that with a white dwarf, what force prevents gravity? So with a white dwarf, what force prevents gravity from collapsing the white dwarf any further? So the white dwarf is held up by I'm writing it down again because it's kind of the key to this, right? Electron degeneracy pressure. So what happens if the electrons are not strong enough? Okay, so why would that be? So what happens if the core is greater than 1.4 solar masses? That's masses of the sun right here. The electron degeneracy pressure is not enough. Is not enough. Gravity is too strong. Okay, gravity is too strong. So what happens then? Well, the electrons are going to be forced into the nuclei where they will find protons. And so what happens is the electrons are going to meet protons in the nucleus. What do you think might happen if you were able to push an electron and a proton together? You do also need one of these to make it complete, but just ignore that. Don't worry too much about that. What do you get? And the answer is you get a neutron. So if the iron core, let me write that down. Iron, remember the symbol is Fe. Iron core is greater than 1.4, then the electrons are going to be forced into the nuclei, and they are going to form neutrons, which are neutral, right? A negative plus a positive makes zero. Neutral neutrons. Okay, this is a pretty big deal. Okay, I'm kind of excited to share this with you. This is amazing. We have just created a giant ball of neutrons. It's like a single atomic nucleus, and there is nothing in the universe that we have ever seen more dense than this. This is truly incredible stuff. What do you call this weird thing, which is just a ball of neutrons? What should we call it? And the answer is a neutron star. All right, so here it is, the neutron star. Because the electron degeneracy pressure fails, the electrons are going to be forced together to form a neutron star. Now, remember the antineutrino? The way that it goes in is if a neutrino comes flying out at the same time. So this event, this is going to be a supernova, a type 2 supernova, creates a huge number of neutrinos. And this is actually an exciting thing. This is one of the exciting things that's happened in recent time. Actually, it hasn't happened too many times in my life, but when I was a physics undergraduate student in 1987, something amazing happened. Some neutrino detectors, the Kamiokanda detector in Japan actually is the one that I remember, the Super Kamiokanda, detected a strange thing where there were multiple neutrino events in a single day. And they figured out where it was coming from, and they told the astronomers, hey, we're not sure what's going on, but look in this direction. And when astronomers turned their telescopes, they saw a brand new supernova had just gone off. So the neutrinos got there. Remember, neutrinos fly out of the sun without stopping. So they fly out of the exploding supernova without stopping too. Whereas the light gets trapped at first and takes a little while before it can finally escape. So the neutrinos get here, and then the light gets here, which is kind of a neat thing. It was the first time we had ever seen neutrinos indicate that a supernova was about to occur. But we're looking for this, and in fact, we're hoping that we'll be able to see this in the future. So this was the simulation I mentioned for you. It's pretty complicated. But in fact, supernovas are incredible. This is an event that is very special. They're happening all over the place in the universe every night. They're actually, supernovas are happening all the time, but they will briefly light up in a galaxy and then fade away after a while. But they are truly incredible. So I actually feel like I should pause for a moment and tell you a little story. If you remember, there was the story of the supernova, the guest star of the year 1054. Let me see if I can bring that back up for you. Let's see. Hold on one moment. Okay, I can't find it, but let me just bring it up. Oh, I see why. That's because I didn't go back to that. Okay, here we go. Let me go bring up my my chapter 13 support material, chapter 13. And I'm actually going to go ahead, and I wasn't going to do this, but I feel like I just want to tell you a little story. But this is the supernova 1054, just to remind you. This supernova, this was the first time we had seen or suspected that stars died. Okay, and so let me tell you how the story works, right? So actually this thing called the Crab Nebula, which is also known as M1, right? M1 means Messier object number 1, was visualized actually. So first of all, Charles Messier saw it. And then in the year, let's see, what year was that? In actually in the 1800s, sorry, the 1800s, it was first seen, and actually they thought it looked like a crab. But in the early 1920s, right, somebody says, hey, that thing is growing, it's getting bigger. And so this expanding cloud was getting bigger, right? So as soon as they saw this, they tried to figure out, well, how fast is it expanding? And based on the rate of expansion, they imagined playing a film backwards, right? Let's make it get smaller. And they predicted that the time of the event, whatever it was around the 1050s, right? 1050, something like that. And then they went looking to see if anybody had noticed anything unusual in that part of the sky. This is in the constellation of Taurus, the bull. And it turns out that in the year 1054, and I know I've mentioned this before to you, but in the year 1054, Chinese astronomers noticed that a star appeared in that constellation that had not been there before. Here's where it is at the end of the horns of Taurus, the bull. Here's the eye of the bull, Aldebaran. And then, so the interesting thing, that star was visible during the daytime for 3 weeks, and then at nighttime for 2 years. So that's what supernovas can do. Now, since then, there have been a couple of other situations, but really not too many. So what's really fun for me to know is that in the next years in my life, there certainly will be another one probably, or hopefully there will be one. It's time for one. Kepler saw one too, by the way. It's called Kepler's star. But again, there's only been a handful of them since we've noticed that stars die. And so it's very likely that in your life, you will get the news that we see a new supernova, and let's go look at that. That star wasn't there yesterday, and it'll fade away after a couple of years. Okay, so supernova remnant. Okay, so supernova is pretty cool. Type 2 supernova, a star that went all the way to iron and then exploded. How much mass does a type 2 supernova have? I have no idea, right? I just know that it started with more than 8, okay? So it's just a big deal. This is a giant thing. Oh, this is actually, I have this. Okay, so Crab Nebula, M1 is a type 2 supernova remnant. Astronomers discovered the nebula was expanding and calculated the explosion, went back to the year 1054. And this is what I just told you. Okay, so cool. So what's the difference between a nova and a supernova? If you remember, a nova happens because of a white dwarf with a symbiotic binary, with a red giant or red supergiant that's feeding it. And this is a little flash. It's tiny. A supernova is huge, right? It's an enormous explosion. The novas are short-lived, but they happen time after time after time. And what happens every single time? Well, you might remember that when you dump a little bit of matter on a white dwarf, it explodes in a shining light called a nova, and then the white dwarf gets a little bit more massive. Now, this wouldn't be a big deal, except you remember that we just mentioned a few minutes ago that white dwarfs have a maximum mass called the Chandrasekhar limit. So now imagine that you are a white dwarf and your mass is 1.39 solar masses. Hey, everything's fine. The electron degeneracy pressure is fine. Got it. We got it. No problem. I got you. Okay, and then nova, 1.395, 1.399, right? Imagine that one day, that little extra bit of matter that gets dumped onto the white dwarf causes it to exceed the Chandrasekhar limit. What happens now? Well, so you want to understand that what happened was the electron degeneracy pressure was strong enough, and suddenly it isn't strong enough anymore. So what happens? Gravity wins. It collapses and heats up, and almost simultaneously, all of that material that was just inert and ash, I told you couldn't fuse, becomes hot enough to fuse, and you get a runaway fusion event, and we call that a type 1a supernova, okay? So we think that this is how it happens, right? That a red giant next to a white dwarf and keep feeding, everything's fine until the day that it goes above the Chandrasekhar limit, 1.4 solar masses, and then that white dwarf explodes in a supernova. Very, very exciting. So runaway thermonuclear fusion, all of that material that was just inert, it couldn't function as a fuel, is now going to be hot enough because of that extra collapsing. Okay, so Chandrasekhar limit, it ignites and all of that explodes. You get a type 1a supernova. Okay, so a type 1a supernova is produced by the thermonuclear explosion of a white dwarf that has accreted mass from a binary companion, causing it to exceed the Chandrasekhar limit. So it's more complicated than our class needs to worry about, but it's pretty exciting. It also is a very special event, and we can see new stars appear and then fade away. And actually, so this is an important idea. What is the mass of a type 1a supernova? And the answer is, well, 1.4 solar masses. Okay, every single time, if this is the way it's happening, then it's that white dwarf has just gone over the Chandrasekhar limit. And so they have the same mass every time they explode. So actually, you want to make sure you know that type 1a supernovas are an excellent standard candle. Okay, so what is a standard candle? Let me remind you. It's where you know the absolute magnitude of the event or the star, right? Star or event, in this case is a supernova. And you measure what it is, the apparent, so you know the absolute magnitude, you measure the apparent magnitude, you compare them, and you calculate the distance, right? So using this technique, we've been able to measure distances to other galaxies, and it is really one of the most powerful ones. Okay, we'll learn more about that later. Okay, so of course the white dwarf is ripped apart, and in many cases we think also the companion gets ripped apart and actually makes an interesting kind of change that might be detectable in the explosion. So the main explosion, then there's a secondary kind of explosion that occurs. So this is the part that I think is a little confusing, right? Where does all the light come from? And in both cases, type 1a and type 2 supernova, you might think it's just from the main event. Well, that turns out to not quite be right. It turns out there's a cloud of material expanding away from the explosion, and that material has been enriched by particles, by protons, by neutrons, by alpha particles. And actually, in many cases, it has grown, it has jumped up to higher atomic numbers and become radioactive. And so the glow that we see in most of that is actually a radioactive glow from the unstable particles gradually getting rid of their energy, becoming more stable. So the flux of material gets absorbed and taken in by the things that are nearby, and they turn into heavier elements, right? So on the periodic table, a lot of elements are being generated during this process. So I'm going to tell you more about that in a few minutes. Okay, so here is the light curve for a type 1a supernova, and it's kind of it's got a really bright part, and then it kind of fades away. Sorry, it fades away for a while. It's important that astronomers see the peak, or else they can't really say for sure, the magnitude. So you need to know the peak magnitude to be able to use this as a distance indicator. But it is a really exciting thing to notice. Okay, so now we know, first of all, that we have a type 2 supernova exceeds the Chandrasekhar limit. We said that the electrons are forced into the nucleus where they find protons and they form neutrons. Okay, so I left out the antineutrino. I should have put that back in. So what you get is in a type 2 supernova, instead of an Earth-size star thing, you get something, this tiny little thing. Okay, this is about 10 miles across, 20 kilometers maybe, 20 kilometers across. Oh, I put 10 kilometers. Ah, that's 20 kilometers. 10, 20, or something like that. 10 miles, 20 kilometers. Okay. It has a mass, let's say, be more than 1.4. Actually, I should have changed this. I'm going to say up to 2.4 now. We know about one that's 2.4. So what happens is you create a big ball of neutrons. But again, this ball of neutrons doesn't continue to collapse. Something is stopping gravity. In this case, I'm not going to go into all of the discussion, but in this case, it's the actual neutrons degeneracy pressure is what it's called. So if you write that down, neutron degeneracy pressure is what is supporting a neutron star from collapsing any further. Okay. So, but you'll notice that there's a limit to the neutron degeneracy pressure. We don't know exactly what that limit is. So right now, that number should be changed to 2.4 solar masses. Actually, I'm going to go ahead and I'm going to change this because you guys are like, why didn't you change this? And the answer is, I don't know. I should have. I just didn't notice. I messed up. Sorry about that. I'm human. Okay, here we go. I just changed it. So 1.4 to 2.4 solar masses. And it's packed into a tiny little sphere. This is amazing. You have never seen anything. We have never seen anything more dense than this material. It is like a single atomic nucleus, but it's the mass of a star, right? More than the mass of a star. So I'd like to talk to you about that just for a second, just to give you a sense of what that is. The gravitational field is 200 billion, whatever. That's just what, okay. A teaspoon would weigh as much as 100 billion tons. Several times all the people on Earth, 1 teaspoon, okay. But here's a pretty crazy thing. Here we live on a beautiful planet, and I think this example for me really kind of lets me get a feel for how dense this material is. So this is me, okay? It is very difficult for us to understand how matter is mostly empty space. Everything seems solid, but neutron stars are the most densely packed structures we have seen in nature. Imagine that you could take the entire Earth, right, the entire Earth, and compress it down to nuclear densities in the shape of a sphere. How big do you think it would be? Remember, a star gets compressed down to the size of 10 to 20 kilometers. How big is the Earth? Okay, is it 1 kilometer? What do you think? And the answer is the size of a bowling ball. So this blows my mind. If your mind is a little broken right now, that's okay, I'm with you. You could take the entire Earth, and if you squished it down to a neutron star density, it would be the size of a bowling ball. You could hold it in your hands. You'd be ripped apart, of course, by the intense gravitational fields, but it's just amazing, right? The Earth is mostly made of empty space. Atoms are mostly made of empty space. The electrons take up a lot of volume. When you squish them down into the protons, they don't take up very much volume at all. All right, so we do see some interesting things. Sometimes you'll see an X-ray burster is a system that has a neutron star in it and a companion. And the companion is going to give material kind of like we saw with the red giant white dwarf, but now red giant or red supergiant with a neutron star, and you get a very similar kind of mechanism. So I'll talk about that in just a moment. Now, I do want to just mention this is actually a little bit closer to the truth. We don't know for sure how neutron stars work. We don't know. Okay, so if you take a look right here, I don't want you to actually learn any of this, but just look at it and appreciate that this picture tries to illustrate for you how difficult this concept is. And so you've got these maybe on the outer shell, a crust of ions and electrons. In other words, those are still kind of like atoms. And then here you have a bunch of electrons and neutrons. And then here you have the neutron proton Fermi liquid, whatever that means, and some electrons. And then in the innermost part, a quark gluon plasma. Okay, this is exotic. It is way beyond the scope of our course. The only reason I mentioned this to you is just so you understand it's not as simple as a big ball of neutrons. It's much more interesting than that, right? This is something that will keep PhDs growing for years to come. And I'm going to be sharing with you a little bit later that there is a new way to see neutron stars and to understand a little bit more about what's going on. But anyways, neutron stars are probably not just neutrons, but includes exotic materials as well. Okay, so I want to share with you a little story, and that X-ray burster is going to kind of come into focus a little bit, what the heck is going on. But it's the story of Jocelyn Bell. So you need to know her name. Jocelyn Bell and her advisor, Anthony Hewish, detected something very interesting. They detected radio waves, and these radio waves seem to have a very regular period. They were incredibly regular. They had pulses of radio energy, And in fact, at first they thought that they were possibly aliens, okay? And they gave them the title LGM. Anybody know what that means? Little green men, right? Little green men. But later on, we called them pulsars. What is a pulsar? Well, pulsar is a neutron star. But if you remember, stars are usually rotating. What happens when you take the core of the star, which is rotating, and you collapse it down? It has to rotate faster. Anybody remember the name of the principle? Conservation of angular momentum. Same principle, right? And so what has to happen when you create a neutron star, it has to rotate really rapidly. And so we think that actually it looks something like this. So imagine that this neutron star has a nearby companion or a way to feed material in. Then what would happen is an accretion disk would form around that neutron star. And because of the accretion disk and the dynamo effect, you would expect to have magnetic field. And that magnetic field produces jets of material and flashes of energy, high energy photons. So the X-ray burster is coming from the jets that are appearing because of the magnetic field from this neutron star. Okay, I do have a little animation I'll share with you. This is a pulsar animation. And the idea is the pulsar can only be seen if the light that we see happens to be flashing at the Earth. And if it's not, then we don't see it, right? So lots of neutron stars must be out there, but not all of them have magnetic fields. Not all of them are going to be flashing, and the flash has to be pointed at the Earth. So sometimes this is called the lighthouse model, because as it turns like a lighthouse, if the light is flashing towards you, you see it. But if it never flashes towards you, you can't really see it. So it's called the lighthouse model. So if the Earth happens to be in one of these beams, we would see that as a flash. And this is slowed down, of course, dramatically because it's moving really fast. In fact, these are rotating sometimes thousands of times per second. So they're called millisecond pulsars, okay? So these rotations, 600, sorry, I said thousands of times per minute. So 600 rotations per second, okay? So what happens when a massive star dies and the iron core collapses? What do you get? Well, the answer is, well, we talked about one class. If it's between 1.4 and 2.4, you get a neutron star. But what if you have even more mass than that? So the electron degeneracy pressure is not enough, right? Because you went above 1.4 solar masses, the Chandrasekhar limit. The neutron degeneracy pressure is not enough. We don't know the exact number, but let's say 2.4 solar masses. What happens? What stops gravity? And you want to know the answer is nothing. There is nothing that can stop gravity. Gravity wins, okay? Gravity always wins, right? So this is a little summary for you, okay? If the initial mass of the star is less than 8 solar masses, that star will never go beyond helium burning, right? So it'll have a carbon-oxygen core, it'll collapse into a white dwarf, and it'll have a remnant mass less than 1.4 solar masses. It is going to be held up, it's a white dwarf, it's held up by electron degeneracy pressure. If the mass is between 8 and about 20 solar masses, then you get a neutron star with a remnant mass somewhere between 1.4 and 2.4 solar masses. It's held against gravity, or what stops gravity is the neutron degeneracy pressure. But apparently, right now, if you start with more than 20, your core is going to be so big that when you collapse, you have more than 2.7 solar masses. There's nothing that can stop you. You just got a black hole. Okay. So I'm going to share with you, my final slide is a new story that's brand new. In 2017, we saw the first example of it. It was the merger of two neutron stars. And actually, really amazing. It turns out that we're going to be learning about this, that the neutron star merger caused ripples in space-time. Okay, so I actually, again, I shared this with you, but I do want to just show it to you because it's short. I love the Spanish. It's actually Portuguese, I think, but it doesn't matter. Ignore this, the writing. This was the best version I could find. There's even music. And here they are, neutron stars that are merging. And the reason they're merging is they're losing energy. And you might be like, well, that's not possible. But the answer is yes, they can, by making ripples in space-time. That energy of the waves of rippling space-time, called gravitational wave, allows them to get closer and closer together. So they spiral closer and closer together, and they collide, and they smash into each other. So this is actually the very first time we have ever seen it. The merger of two neutron stars produces an explosion 1,000 times as powerful as a regular nova, and therefore it is called a kilonova. So this is the first kilonova. This is amazing. We just saw it a few years ago for the very first time. So it'll be 3 years in August, the very first one we have ever seen. And so this is the part that I think is so amazing. And please, I know you've watched the video, or you will watch the video shortly. But our friends in Galita at the Las Cumbres Observatory made actually one of the most significant contributions to this. They were able to watch the event from the brightest part, right, the peak of the light curve, and it faded away. And if you look right here, that's 4 days. This is an incredibly short event, short-lived event. It's called a transient event. And the gravitational waves were also accompanied by a gamma ray burst at the same time. And the answer was, how is it possible that they get, well, because they came from the same event. And astronomers for the very first time saw this. Okay, so this is a big deal, and it happened in your life and my life, and it's actually changing astronomy. So it's two different techniques for being able to feel and see the universe. You feel the shaking of space-time through what's called a gravitational wave observatory, and then you see the light with an X-ray telescope. Okay, X-ray cameras mounted on the telescope. And so this is called a multi-messenger event, and there are only a couple right now. And this is a very exciting thing, but we do think that it's going to be a future thing that we'll hear about. Now, I'm going to save it till next lecture, but when the two neutron stars merged, the mass of the merged object was 2.7 solar masses. So what do you get when you put together 2.7 solar masses? Okay, so I kind of gave it away. But the answer was, we didn't know for sure. In fact, theoreticians thought it would either be the most massive neutron star we'd ever seen, or the smallest mass black hole we'd ever seen. Could be either one. Either one is a win, right? We win no matter what. And now I'm going to reveal next time what it was, okay? But you might be able to figure it out. Okay, so the last slide, my very last slide, I want to just share with you. Again, you don't need to understand everything about this, but there's a process that we call stellar nucleosynthesis. So I mentioned to you a while back when we started talking about the sun, that stars are element factories. They're creating new elements by fusing atoms together. But that turns out to just be a tiny part of the story. And I have to be honest too, that up until a few years ago, I didn't understand most of what I'm about to show you, okay? So again, don't worry about understanding everything, but look at the colors. This is so cool, right? Start with the blue, the Big Bang, right? If you look right here, you see there's hydrogen and the helium and a little tiny bit of lithium. And that might actually be wrong, but anyway, the main thing that the Big Bang created was the fuel that all stars will eventually use, the hydrogen and the helium, right? That was created in the Big Bang. Most of that hydrogen and helium came from the Big Bang. But let's look at some other little things, right? So we have dying low mass stars. That's like our sun, right? They produce elements. That's kind of interesting. So the process of shooting out waves of material and the white dwarf, I guess that's kind of, it's a less energetic process, but it certainly does. And then we have exploding massive stars. What does that mean? Type 2 supernova, right? And then we have the white ones right here, or the grayish ones. That's exploding white dwarfs. That's a type 1A supernova. And here we have the newest one, 2017, merging neutron stars. I want you to look at all the purple. And I want you to understand that if you look for elements like, you guys know this element, AU. Anybody know that element? Gold. And how about this AG? Silver. How about this PT? Platinum. Most of those materials were created in events like this one that we saw in kilonovas, right? In mergers of neutron stars, these heavy elements are being produced. Now, I have to be honest, I don't think the story is over because there's a whole class that is not mentioned here. And I think we're beginning to see examples of other things that will be on the chart in a few years. But right now, this is the best we have. It's good enough. If you want me to mention, the thing that I don't see here is the merger of two white dwarfs, which I just started hearing about this. Don't think about this. But anyways, there's one more I didn't mention. It's called cosmic ray fission. And the upper atmosphere of the Earth, beryllium and boron, which are mostly unstable, are being made in the upper atmosphere when cosmic rays hit the upper atmosphere. Okay, so that's my lecture for chapter 13. Please watch, after you've watched this, you can now take the quiz, read the chapter if you want, look at the other little thing, and then take the test.